Ever wondered how AI models like GPT or BERT understand language so effectively? The answer lies in a revolutionary architecture called the transformer. Today, we're diving deep into the technical heart of transformers, exploring self-attention mechanisms, positional encodings, and why they've become the cornerstone of modern NLP. If you're a developer, researcher, or just curious about the math behind AI, this is the breakdown you've been waiting for. Before transformers, recurrent neural networks (RNNs) and convolutional neural networks (CNNs) dominated sequence modeling. But they had critical limitations. RNNs struggled with long-term dependencies due to vanishing gradients, while CNNs relied on fixed receptive fields, making them inefficient for variable-length sequences. These bottlenecks demanded a new approach, one that could process entire sequences in parallel while capturing complex dependencies. Enter the transformer. The transformer replaces recurrent layers with a self-attention mechanism, allowing the model to weigh the importance of different words in a sequence. At its core are three components: query Q, key K, and value V matrices. For each word, the model computes attention scores by taking the dot product of Q and K, scaling it by the square root of the key dimension, and applying a softmax to normalize. This process generates a weighted sum of V matrices, producing context-aware embeddings. Think of it as the model dynamically focusing on relevant parts of the input, like a human reader highlighting key sentences. Let's break this down mathematically. Given a sequence of word embeddings x backslash in backslash math bar n backslash times d, $, we project them into Q, K, V using learned weight matrices. Q xwq, K equals xwk, V equals xwv. The attention weights A are calculated as A equals backslash text softmax backslash left, backslash frac uk t backslash sqrt dk backslash right, $, where dk is the dimension of the key vectors. Finally, the output is backslash text attention, Q, K, V equals AV. This allows the model to capture global dependencies, unlike RNNs, which process sequences sequentially. But wait, how does the model account for word order? Unlike RNNs, transformers have no inherent notion of sequence position. The solution: positional encodings, which add sine and cosine functions of different frequencies to token embeddings. For a position I $ and dimension j, the encoding is backslash text p, I2j, backslash sin backslash left, backslash frac I10002j slash d backslash right, $. Backslash text p, I2j plus 1 equals backslash cos backslash left, backslash frac I10002j slash d backslash right. These encodings enable the model to learn relative positions, ensuring it doesn't treat sequences as unordered bags of words. To capture diverse relationships, transformers use multi-head attention. The model splits Q, K, V into multiple heads, computes attention separately for each, and concatenates the results. For example, one head might focus on syntactic relationships, while another captures semantic meanings. This parallel processing allows the model to learn multiple representations of the same input, enhancing its ability to generalize. Each transformer block also includes a feed-forward network, FFN, a simple two-layer MLP applied independently to each position. The structure is backslash text FFN, X equals backslash text relu, XW1 plus B1, W2 plus B2. These networks introduce nonlinearity, allowing the model to learn complex patterns. Stacking multiple transformer layers enables hierarchical feature extraction, from local to global contexts. Transformers have redefined NLP by combining self-attention, positional encodings, and parallel processing. Their ability to model long-range dependencies and scale efficiently has led to breakthroughs in machine translation, text generation, and more. As research continues, exploring innovations like sparse attention or efficient variants, transformers remain a testament to the power of architectural innovation. If you're inspired to dive deeper, check the description for links to the original paper and cutting-edge implementations. Stay curious and keep exploring the frontier of AI. Got questions about how transformers handle code generation or their limitations in low-resource scenarios? Drop them in the comments. And if you're building your own models, share your experiences. We're all in this together. Subscribe for more deep dives into AI research. Next up, efficient transformers and the future of large-scale models.